Good day and welcome back. In this video, we will begin our discussion of limits and continuity. The overall goal in this chapter of the textbook is to work our way towards differentiation and then eventually properties of differentiation. But in order for us to actually differentiate, we need to introduce the idea of limits from which follows continuity for functions of two variables. To get us motivated for this topic, I have an example that I've taken from the textbook. We have two functions, f and g, and associated with f and g, we have tables of outputs that show us kind of for an input of the form x comma y, what number will be output from the function. So for example, if we look at this 0.841 in the top of the left table of values, that corresponds to an input of -1 for x and 0 for y. And what we would like to do from these tables of values is just make some guesses. As we approach this value of interest, 0, 0, what is happening to the outputs of the function? Now, first of all, I say this is a point of interest because both f and g are undefined at 0, 0 because you are dividing by 0. But the fundamental question still remains, how do these functions behave when you have inputs close to 0, 0? That is, what is the limit as we approach 0, 0? And looking at this table of values on the left, it seems as though as we zoom in closer and closer to inputting 0 for x and 0 for y, we can see those outputs are all getting relatively close to each other. So it appears that the closer we get to this spot where the function is undefined, those outputs are going to get really close to 1. And that's really the idea of a limit. For an input close to the origin, the outputs are going to be close to 1. Now, the idea is similar if we look to the right. If we consider having an input that lies on the x-axis, that would be when y is 0. All of those outputs would be 1. Similarly, if we wanted to have an input lying on the y-axis, so if we make our x value 0, then all of those associated outputs are -1. And note, -1 and 1 are pretty far away from each other. So those values that output from the function are not getting close to any single value. So in this case, because they're not getting close to any single value, we would guess that the limit as xy approaches the origin of this function g, at least based upon the information we have on this table, we would say does not exist. And we can even give some rationale here. We can say because the limits along the x-axis, and remember the x-axis would correspond to y being 0. Those limits would be 1. So the limit along the x-axis given by y equals 0, and along the x-axis, excuse me, the y-axis, which corresponds to x equals 0, they disagree with each other. And we will explore this rightmost function in more detail in an upcoming example. But for now, I think we've gathered the intuition we need to think about what it means for a function of two variables to have a limit. So we will say that the limit as, and I have a small typo here, this should be as x comma y approaches ab of a function of two variables is equal to the number L if the values of the function, so f of xy, become close to L, so we can force those outputs close to L, as the point xy approaches AB, and the key here is along any path. So in our above example, we had approaching 0, 0 along two different paths or curves. one along the x-axis and another along the y-axis, and they disagreed. That indicated that the limit does not exist. And that should remind us of a property that was extremely useful back when we were in Calc 1. So recall from Calculus 1. A key way of showing that a limit does not exist would be looking at the limits as you approach from the left, looking at the limit as you approach from the right. And if the limit from the left and the limit from the right disagree with each other, then the limit as x approaches a in general does not exist. And in terms of a picture representing this, when you're dealing with a function of one variable and you want to know what happens as our inputs approach a, this is a rather boring situation, as we're going to see. You can approach a from the left, you can approach a from the right. And those are the only two directions that you can approach a. So you can only approach a in two directions. And if those limits do not agree with each other from the two directions, that would indicate that the limit itself does not exist. And it turns out we can extend this idea very nicely to functions now of two variables, where our inputs are a subset of the xy plane. So let's just draw a picture to represent this. So in a function of two variables, and we're thinking about a limit as we approach some point a comma b. Now, when it comes to approaching a point in the xy plane, there are all kinds of ways that we could do this. We could approach it via a horizontal line, so that would maybe be something like y equals b. And note, when we talk about approaching along the line y equals b, that really does include from both directions. I typically will only include that arrow from the left just to kind of illustrate the point. Similarly, you could approach this point along a vertical line, maybe something like x equals a. But of course, there's a whole bunch of possibilities. Maybe you approach it along something that's more quadratic looking, or potentially even something that's kind of spiraling around to get in there. There are infinitely many ways that we can approach a comma b. So the big note here is that in R2, so two-dimensional space, we can approach this point of interest in, I'll just say many, and by many I really mean infinitely many ways. But this gives us a really nice way of showing when a limit does not exist. So if two, and I'll call these things paths, have distinct limits, then the limit itself as xy approaches ab of the function will not exist. And this idea is very similar to what we saw back when we were in Calculus 1. If the limit from the left and the limit from the right are not equal to each other, the limit itself does not exist. So same idea here. If you have a limit along two different paths that give you distinct limiting values, the limit will not exist. It needs to have a single value. So let's look at a common example. Let's use the idea discussed on the previous page to show that the given limit does not exist. And let me just note, if you flip back one page, this is our motivating example. And what we noted in the motivating example is that the limit behaved differently along the x-axis and along the y-axis. So what we're going to do is explore two different paths. So in our first path, and you don't have to write P1, but just to kind of illustrate this as nicely as we can, if we say that we are approaching 0, 0 along the x-axis, so that would be y is equal to 0. What we want to do is look at the above limit, and each and every y should become a 0. So this would be x squared minus 0 squared over x squared plus 0 squared. And the key thing we have done is we've taken this limit of a function of two variables and turned it into this more familiar limit of a single variable. And that's key. This is now a familiar limit. This is as x goes to 0 of x squared over x squared, which is the limit as x approaches 0 of 1, and the limit of a constant is always at constant. Now let's consider a second path. Call it P2. And another kind of simple path to choose, since we're approaching the point 0, 0, would be just that vertical line, x equals 0, i.e. the y-axis. So along this path, we would have the limit of 0y approaches 0, 0. So now we want to look at the above limit and make each and every x a 0. So 0 squared minus y squared over 0 squared plus y squared, which similarly becomes a limit of a single variable, y approaching 0 of minus y squared over y squared, which is the limit as y approaches 0 of minus 1, and the limit of a constant is that constant. And what we have nicely illustrated here is we've chosen two paths that approach the origin. One of them is along the horizontal line y equals 0, and the other is along the vertical line x equals 0. And they result in different values. And if you ever have two paths with different limiting values, that tells us that the limit itself does not exist. So the last thing we need to do is give our conclusion. We have all of the work out of the way. Make sure we write down kind of what this work tells us. The conclusion, therefore, this limit of interest, and we always need to rewrite this down so we know specifically what limit we are talking about, does not exist. And a common question I would typically get at this point in class is, what type of work do we have to show? Well, at a minimum, I want you to tell me what each path is. If you're going along the line y equals 0, specifically write that out. Specifically write out x equals 0. Use good notation in terms of limits, equal signs at each step until that limit is evaluated. Then to conclude, make sure you tell me what limit you are evaluating and what your conclusion is. In the next video, we'll explore several more examples. So stay tuned and take care.